Evening, anywhere you are watching. So, welcome to another edition of NAMSSN tutorial. So, my name is Kamal, and today we are looking at series solution of ordinary differential equation. So, in some of our videos, we have talked about how to use power series to solve second order differential equation, the idea of ordinary point and singular points, regular singular and irregular singular points. So you can just check our previous videos and watch it. So today we want to move to another techniques, so which is known as Frobenius method. So let's go back to ordinary points and singular points. So we define an ordinary point. A point x equals to x naught is an ordinary point if the differential equation p of s do not turn to infinity at that point. So what I mean is when we have d square y dx square plus p of x dy dx plus q of s equals to 0. Now, so suppose we have a point x equals to x naught. So if the limit at point x equals to x naught of this p of x now, it gives us 0 or any number other than infinity. So then we say that that point is an ordinary point. So today now I want to look at solution when x equals to 0 is the ordinary point. So that is what we call Frobenius method. So let's look at some examples. We have, let's solve by power series 9x into 1 minus x d square y dx squared minus 12 dy dx plus 4y equals to 0. So we want to use Frobenius method to solve this differential equation. So first thing we are going to do is to expand where necessary. So solution we are going to have, this is 9x, permits me to be using y double prime, so that's convenient for me. So 9x y double prime, 9x times x, that's 9x square y double prime minus 12y prime plus 4y equals to 0, right? Then we'll say the solution we are going to use, we are going to say let's y be summation n from 0 to infinity a n x raised to power n plus r. So unlike power series in our previous video, I only use summation a n x n. So a n x n. So for Frobenius method, it will have n plus r. So then we differentiate. So what is dy ds? If you differentiate this guy with respect to n, you know this power will come here, it will turn to summation n from 0 to infinity n plus r a n x raised to power n plus r minus 1, okay? And if you differentiate again, it will be summation n from 0 n plus r minus 1. Like this power will come here, a n x raised to power n plus r minus 2, right? So we only need first and second derivative, okay? Now, what do you observe? We observe that the limit of this sum is not changing. Like the limit is from 0 to infinity, 0 to infinity, 0 to infinity. Why? You know, if I have y, let's say we have a series y equals to a naught a1x a2x square, like that. If I take the derivative of this series now, if I differentiate with respect to s, a naught will be 0, a naught is a constant, so then we are going to have a1 plus 2a2x, like that. So that means if I'm using power series, y equals to summation a n x n, just summation a n x n, the limit will be changing. One will start from 0, the next one will start from 1. So if I differentiate this guy again now, a1 will now be a constant. The derivative of constant is 0. So 2a2, like that. So that one will be changing. But if I have y equals to a naught x, a1x squared, let's say we have it like this, x r into a naught plus a1x a2x squared. This kind of series now. If I have x, r, and some node. So if I take the derivative, what is dy dx? No, if I differentiate, this is like a naught xr, a1 xr plus 1, a2 xr plus 2, like that. So if I differentiate this guy now, it will be r a naught xr minus 1. Differentiate again, it will be r plus 1 a1 xr. Oh, this is xr, like, right? So if you differentiate, so what you observe is that a naught will still be there. If you differentiate with respect to x, that a naught will still be there. If you differentiate again, a naught will be there again. So that is why for Frobenius method, this n plus r that you've introduced now, the limit will still start from 0, from 0, from 0, from 0. What I'm saying is, if you have a series a naught, a1x, a2x squared, you know this is like an xn, right? Like the summation now. If you differentiate this thing now, it will start from 1. The first node, these are node, okay? The first node will be eliminated, a naught will be 0. It will start from a1. Like dy dx will be summation n from 1, a1, whatever, whatever, like that. If you differentiate again, if you differentiate from a1 now, no, if I differentiate, I'm going to have a1 plus 2a2x, right? If I differentiate this thing again, a1 will now turn to 0. The next one will start from a2. So that is using power series. But this time around, we are using Frobenius method. It's having n plus r. So that r will make sure that the limit starts from 0, okay? So that is it. Then after getting the 3 derivatives now, then we substitute for y prime prime, y prime and y into the problem we are solving. What are we solving? We are solving this. Let's say into equation 1. Substitute for y prime, y double prime into equation 1. This is my equation 1. Sorry, I'm using this. So equation 1 is 9x y double prime. So summation n from 0 to infinity of n plus r minus 1 a n x raised power n plus r minus 2, okay? Minus 9x squared summation n from 0 to infinity. Y double prime again is n plus r minus 1 a n x raised power n plus r minus 2, right? Then 12y prime minus 12 summation n from 0 to infinity. Y prime is n plus r a n x raised power n plus r minus 1. 4y. What is y? This is y, okay? 4 summation n from 0 to infinity. A n x raised power n plus r. All of them equals to 0, all right? Then x times x raised power n plus r minus 2. This is x raised power 1, right? This is indices. N plus r minus 2 times 1. That will be n plus r minus 1, okay? So this will be 9 summation n from 0. Nothing will happen to summation, okay, of n plus r minus 1 an x raised power n plus r minus 1. That's how it's going to be. Then this next one, minus 9. This is x squared. X squared times n plus r minus 2. 2 cancel 2, okay? So minus 9 summation n from 0 to infinity of n plus r minus 1 an x n plus r, all right? Then minus 12. Oh, this one does not have any x, so you write it like that. Minus 12 summation n from 0 to infinity n plus r an x raised power n plus r minus 1, right? And last one here too does not have any x, so we say plus 4 summation n from 0 an x raised power n plus r, all of them equals to 0. After that, the next thing we need to look into is the power of x. So this one is having x raised power n plus r minus 1, x raised power n plus r minus 1, n plus r. Now we must make sure that this one that is having n plus r minus 1, we are going to force it to be the same power as this n plus r. So what we are going to do is that now, so let's go back to summation. If I have summation, let's say 1 over n plus 1, we have something like this, n from 0 to infinity now. If I say that let n equals to n plus 1, if I make this summation, let n equals to n plus 1, what will happen to this summation now? Of course, anywhere you see n, it will turn to n plus 1. This one will be 1 over n plus 2, right? But what about this lower limits? If n is 0 here now, and we are assuming that n equals to n plus 1, so it is going to be 0 equals to n plus 1, n will be minus 1. it means that this summation will start from -1, and we don't want that. So rather, what we are going to do is that we must avoid having negative number at this lower sum. So we are going to count. So if you can just go back and watch our lectures on power series. So when you have something like this, you count forward. So this one now, this guy, this third sum and fourth sum, I'm going to count for n equals to 1. Sorry, for n equals to 0. So you say count for n equals to 0 in the first and which one? And the third sum. Okay. So if I count for n equals to 0 here, if I count for 0, anywhere you see n, put 0. If n is 0 here, this will be 9r. If n is 0 here, r minus 1. If n is 0 here, a naught. If n is 0 here, x raised to power r minus 1, alright? For the third sum as well, if I put n at 0, if n is 0 here now, it will be minus 12 r, put n at 0, a naught, put n at 0, xr minus 1, okay? So it's just like when you have something like this, 0, 1, 2, 3, 4. You are going like this. No summation now, you are discretizing. You are moving by with space of 0, 1, 2, 3. It's length of 1. Now, if I'm here now, if I'm at n equals to 0 and I jump to n equals to 1, it means that the next counting that I'm going to do will start from 1. If I have 1 plus 2 plus 3 plus 4, I have something like this. And I've already counted 1 plus 2, for example. It means that I already assume that this 1 plus 2 is 3. Then the next one will start from 3. So if I count for n equals to 0, the next limit now will now start with n equals to 1. If you count for n equals to 0, the next one will start from n equals to 1, 2, 3, like that. So if you count for n equals to 0 in the first and third sum, you are going to have this. So you equate it to 0. That is what will give you what we call indicial equation. Okay? So this thing that you count now, equate it to 0. If you equate it to 0, factorize, this will be 9r into r minus 1 minus 12r of a naught x raised to r minus 1 equals to 0. Okay? Equate that one to 0. Don't forget, a naught is the initial condition, is not 0. So, you know, when you have something like this, 2 times something equals to 0. When we say 2 times something is 0, what does that mean? It means that obviously this one is not 0, 2 is not 0. It means what is here that is missing is the 0 part. So when you have 9r minus 1 minus 12r multiplying a naught and something is 0, it means that this part is not the 0 part, because a naught is known, it's constant. So this one is not 0. It means that this 9r minus 1 is 0. So you say that 9r minus 1 minus 12r equals to 0. So you factorize and solve. So this is what we call indicial equation. What do we want to use it to do? Don't worry, when we get it. So indicial equation. So factorize this, we are going to have 9r squared minus 12r minus 9r. So that will be 9r squared minus 21r equals to 0. Solve this. 3r into 3r minus 7 equals to 0, r equals to 0, or 7 over 3, okay? Now keep that. Now go back to the series. So we've already counted for n equals to 0 here now. So the series will now start from 9 summation n from 1 to infinity of n plus r minus 1, a n x raised to power n plus r minus 1. We are still having that power, okay? So minus 9 summation n from 0. We did not touch this one, so that one will still be from 0. Of n plus r minus 1, a n x raised to power n plus r, okay? And this one, we've already counted for n equals to 0. It will now start from 1, the third sum. So minus 12 summation n from 1 to infinity of n plus r, a n x raised to power n plus r minus 1, okay? And the last one, we did not touch that one. Plus 4 summation n from 0, a n x raised to power n plus r, all equals to 0. So what's the next thing to do now? Then, if this series is starting from 1 now, we can now say that let n equals to n plus 1 in the first and which one? And the fourth and the third sum. So that all of them must have the same power of x raised to power n plus r, x raised to power n plus r. So if I now say let n equals to n plus 1, now you know it is easy. A sum that is starting from 1. Well, I don't care whatever the sum is having. So if I say let
n equals to n plus 1. This sum that is starting from 1 now, this one, you say this is 1, 1 equals to n plus 1, it means that n is 0. The sum will now go back to 0, which is what I was avoiding before, that I don't want to have minus 1. The sum must not start from minus 1. So it is starting from 0 now. It makes sense. It means that this sum will now start from 0. This one too will start from 0. Okay? So let n equals to n plus 1 in the first and the third sum. In the first sum, anywhere you see n, put n plus 1. So this will be 9 summation. So if n is n plus 1 here, this one will start from 0 to infinity. Anywhere you see n, put n plus 1. That will be n plus r plus 1. Put n plus 1 here. It will just be n plus r. Okay? N plus 1. If n is n plus 1, n plus 1 plus r minus 1, that's just n plus r. Okay? So if n is n, in first and third sum alone, so leave the second sum, minus 9 summation n from 0 of n plus r minus 1, anx n plus r. Okay? So in the third sum, if n is n plus r minus 12 summation n equals to 0, n plus r plus 1, an plus 1, xn plus r. Alright? And this one, plus 4 summation n from 0 of anx raised by n plus r equals to 0. They are now uniform. Right? N plus r, n plus r, n plus r, n plus r, and all of them are now starting from 0, 0, 0. So let's now collect like term and make an plus 1 the subject. That is our end term. So the one with an plus 1, now these two guys. So I can say that, okay, let me factorize them. Summation n from 0 to infinity. This one is having n plus r plus 1, n plus r plus 1, n plus r plus 1, into, this one will remain 9 times n plus r, alright? And this is minus 12, just minus 12, because I factorized these two guys. Okay, so an plus 1, xn plus r. The rest that are having just an, move all of them to the other side, is equals to, if this one goes to the other side, it will turn to plus, this one will turn to minus. If you factorize them, so are they having anything in common? Only an and xn. Alright. Summation n from 0 to infinity, 9 across to the other side, that's 9 into n plus r, and n plus r minus 1. Okay? 4 across to the other side is turn to minus 4. Well, all of them are just having an xn plus r. You get my factorization, just move them to one side. So what is common now? Xn plus r is common to xn plus r. They will cancel out. Summation, cancel summation. So what do we have? We have n plus r. We have n plus r plus 1. What is 9n plus r? That's 9n plus 9r minus 12. Okay, 9n plus 9r minus 12 of an plus 1 is equals to, so this is 9n plus r, n plus r minus 1 minus 4. All of them of what? Of an. Does that make sense? Now make an plus 1. Divide both sides by all this. You divide both sides by everything here now. You are going to have your an plus 1 as what? An plus 1 equals to 9 into n plus r minus 1 minus 4 all over n plus r plus 1 times 9n plus 9r minus 12 of an. Alright? Because an is there. Now, this is where our initial equation will now be useful now. So, Frobenius method, we are going to have two solutions. Okay? So this, for r equals to 0, will serve for one solution, and for r equals to 7 over 3 will serve for another solution. So from here now, so I'll now say when r is 0, from the solution of my initial equation, when r is 0, so what are we going to have? We are going to have an plus 1. Anywhere we see r, put 0, if r is 0 here, if r is 0 here. So this will be 9n, okay, n minus 1 minus 4 all over, put 0 here, put 0 here in place of r, n plus 1, 9n minus 12 of an. So this is our end term. This is our end term. Well, is there anything we can do to this one? Well, if you want to factorize it further, that's not a problem. Okay. So you now say when n, now start writing your solution to get a1, a2, a3, a4. So when n is 0, now what is our a1? No, if n is 0, yeah, this will be a0 plus 1, a1. If n is 0, 0, 0, 0 will affect this one, it will turn to minus 4. Put 0 here, put 0 here. This will be 1 and minus 12, minus 12. If you put 0 here, a naught. What is minus 4 over minus 12? That's 1 over 3. It means that a1 equals to 1 over 3 a naught. A naught is constant. Then when n equals to 1, if n is 1 here, what will happen? This one will be a2, right? If n is 1, well, 1 will turn everybody here to 0. We are going to have minus 4 over, if n is 1, 1 plus 1, 2. 9 minus 12, minus 3. Oh, so yes, minus 3. And this one will be a1, okay? And what is our a1? We've gotten a1 before. a1 is 1 over 3 a naught. So this is a2 equals to 2a1, 2a2, minus cancel minus 2 over 3. a1 is already 1 over 3 a naught. So all our answer will be in terms of a naught, a naught, a naught. Unlike normal power series, our answer will be in terms of a naught and a1, a naught and a1. So a2 is equals to 2 over 9 a naught. Okay? So you can generate more. Generate for n equals to 2. You have your a3 equals to something. But because of time, so I will stop at a2. Then you write the solution of that one. What is the solution of that one? For r equals to 0, the solution is y equals to what? Summation. Okay, let me do it for the other one too, so then I'll write them together. Now when r equals to 7 over 3, this is where I'm going to use calculator. So when r equals to 7 over 3, put 7 over 3 into this recurrence formula. So it will be an plus 1. If r is 7 over 3, okay, 7 over 3, let's put 7 over 3. So we are going to have 9 into n plus 7 over 3. If you put 7 over 3 here, it will be n plus 4 over 3 minus 4 all over. You put 7 over 3, yes, that's 10 over 3. Okay, so this will be n plus 10 over 3. If you put same thing here, 9n plus 9. Everybody here is having an, don't forget. Then you can now write the solution of that one for n equals to 0 and for n equals to 1. So for n equals to 0, what is a1? What is a1? a1 equals to, if n is 0, if you put 0 here, if you put 0 here, if you put 0 here, put 0 here, if you put 0 here, everybody here will be 24 in the numerator, 24. If you put 0 here, if you put 0 here, 30 a naught, 4 over 5. So a1 equals to 4 over 5 a naught. Okay, so I will do for n equals to 1. I have calculator, don't worry. So just press calculator here. So this will give us a2. If n is 1 here, put 1, put 1, put 1, put 1. Everybody here is 66. Everybody here is 78 a1. That's 11 over 13 a1. And what is a1? 4 over 5 a naught. 44 over 65 a naught. So I'll stop there. So what is our solution from the beginning? Y equals to what? Summation a n x n plus r, abi? And we have two r. R is 0 and r is 1. So it will now be two solutions. Summation n from 0, a n x n plus 0 for r equals to 0. Then plus summation a n x n plus 7 over 3. Does that make sense? The other value of r. Then you expand. If you expand this, a naught, a1, a2, y equals to, for n is 0, this will be a naught, right? For n is 1, this will be a1 x, right? Let me say plus dot 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 like that. The first solution. I think I did it up to a2. So this will be a2 x squared. Then the other one here, it will be plus, when n is 0, this will be a naught x 7 over 3. When n is 1, a1 x 1 plus 7 over 3. If n is 1, if you plug 1 here, 1 over 3. A1 x raised to power 10 over 3. When n is 2, 13 over 3. A to x 13 over 3 plus dot dot dot. Okay, so let's put the limit from 0 to infinity, from 0 to infinity. Alright, so y equals to, what is a naught? A naught is a naught. That's not a problem. A1 is what? For the first one, 1 over 3 a naught. I will factorize. Okay, don't worry. What is a2? A2 is 2 over 9 a naught x squared plus dot dot dot. Then plus the other one now. A naught x 7 over 3. A1 is what? A1 is 4 over 5. 4 over 5. A naught x 10 over 3. A2 is 44 over 65. A naught x 13 over 3. Then plus dot dot dot. What do you observe? A naught is common. A naught is common. Factorize A naught. So A naught into 1 plus 1 over 3x plus 2 over 9x squared. Then plus A naught into what again? X raised to power 7 over 3. And this is 4 over 5. Let me put that one here. Plus 4 over 5. Oh, A naught is also common. 4 over 5. Oh, sorry, x raised to power 7 over 3. 4 over 5. X raised to power 10 over 3. 44 over 65. X raised to power 13 over 3. And all that. Sorry, don't mind my handwriting. So that is how the solution would be. Two solutions. Because why is it like this? Don't forget, you are solving what? Second order differential equation. It will have two solutions. One like this, the other one like this. So that is how that example will be. The algorithm is let y equals to summation NAMSSN plus r. It follows the same algorithm. The one that the power of s that you observe, that probably that one is having xn minus 1. You make sure you force it back to xn. Okay, so that is it. So let's look at another example.
So let's do the same with this problem. Let's solve this. Oh, this is 2x squared y double prime, right? Plus 2xy double prime plus 3xy prime plus 3y prime minus y equals to 0. Okay, then you start by saying let y equals to summation n from 0 of a n x raised to power n plus r from 0 to infinity. If that's the case, what is dy dx? We differentiate this to be n from 0 to infinity. N plus r will come here. N plus r a n x raised to power n plus r minus 1. And what is y double prime now? If you differentiate this guy again, it will be summation n from 0 of n plus r minus 1 a n x raised to power n plus r minus 2. So then you substitute for 1, 2, 3 into this problem we are solving. So it will be 2x squared summation n from 0 to infinity of n plus r minus 1 a n x raised to power n plus r minus 2 plus 2x summation n from 0. Please let's be careful while doing the substitution. This is 2xy double prime again. Write this thing again. N plus r minus 1 a n x raised to power n plus r minus 2 plus 3x summation n from 0. This time around, this is y prime n plus r a n x raised to power n plus r minus 1. Then plus just 3y prime. 3 summation n from 0. Y prime is this n plus r a n x raised to power n plus r minus 1 and minus y. That is minus just y minus summation n from 0 a n x raised to power n plus r equals to 0. So indices, this is x squared. X squared times x n plus r minus 2. So it will be n from 0, n plus r minus 1 a n x raised to power n plus r. Okay, then plus 2x times this guy. So it will be 2 summation n from 0 n plus r minus 1 a n x raised power n plus r minus 1. Okay, x times x raised power something minus 1. It will be 3 summation n from 0 n plus r a n x raised power n plus r. Okay, this is 1, this is minus 1, and 3. This will be 3 summation n from 0 of n plus r a n x n plus r minus 1 minus summation n from 0 of a n x n plus r, all equals to 0. Okay, so this second summation now is having x raised power n plus r minus 1, and the fourth one as well is also having n plus r minus 1. Then we are going to treat that one first by counting for n equals to 0. Then the sum will shift to 1. Then we'll reverse it back again to n is 0. Okay, so what we are going to do is that we are going to count for n equals to 0 in this sum. Why? Because it's having n plus r minus. Oh wait, I think if I say let n equals to n plus 1, well, it will not work. So we are still going to count. So we say that count for n equals to 0 in the second and which one? Second and fourth sum. In the second and fourth sum. If you count for n equals to 0 in the second and fourth sum, so if n is 0 here, just count. We are not writing this series again, just count. If you count for n is 0 here, that will be 2 times r. Okay, if n is 0 here, r minus 1. If n is 0 here, this will be a naught. If n is 0 here, xr minus 1. Okay, plus the sum. Now you are adding. If you count for n equals to 0 here, this will be 3 times r a naught xr minus 1. You equate it to 0. That one that you count, you equate it to 0. When you equate it to 0, that is what will give you what something we call indicial equation. So what is the indicial equation here now? If you add them up, 2rr minus 1 plus 3r, all of them are having a naught xr minus 1 equals to 0. Then this guy is not 0, like I explained in the previous example. This guy is not 0, then you have 2r squared minus 2r plus 3r will be the 0. So that is 2r squared plus r equals to 0. If you solve this, r into 2r plus 1 is 0, r equals to 0 or minus half. So these are the solution of the indicial equation. This is what we call the indicial equation. Indicial equation. So after getting the indicial equation, now go back to the sum. Go back to this sum. Don't forget that we've already count for n equals to 0 in this second and fourth sum. That means they will now start from 1. We count the 0. So it means that we are going to have summation n from 0. This one is not affected. N plus r minus 1 a n x raised by n plus r. Now 2 summation, it will now start from 1 this time around, of n plus r minus 1 of what? A n x raised power n plus r minus 1. Then the third one will be 3 summation n from 0 n plus r a n x n plus r plus 3 summation n from 0. Now it will now start from 1 to infinity of n plus r a n x n plus r minus 1, then minus summation n from 0 of a n x raised power n plus r, all equals to 0. Okay, so after shifting now, then we can now say that let n equals to n plus 1 in these two guys that is affecting the problem. So let n equals to n plus 1. If you say let n equals to n plus 1 in the second and that fourth sum that we are changing now, it will go back to 0 easily, and then this power 2 now will then turn to n plus r, n plus r, n plus r. Then it will be uniform. Okay, so you now say let n equals to n plus 1 in the what? In the second and fourth sum. So the second sum now, why is it the second and fourth sum that I'm talking about so far? Is because it is those two guys that is having n plus r minus 1. So we want to make sure that they are also having the same power as the other one, n plus r, n plus r. So this part we are going to write this again, n equals to 0 to infinity n plus r minus 1 anx n plus r plus 2 summation. Now if n is n plus 1 here, now the sum will now go back to 0. Okay, anywhere you see n, change it to n plus 1. This is n plus r plus 1. Anywhere you see n, change it to n plus 1, n plus 1, n plus r. That is just n plus r. Okay, what I'm saying is, if you say n equals to n plus 1, now you know this one will cancel to turn to just n plus r. You get? So an will be an plus 1, xn plus r, whatever will turn to xn plus r. Okay, and this will be 3 summation n from 0 of n plus r anx n plus r plus 3 summation n from 0 now. Instead of 1, it will now start from 0 to infinity. So this will be n plus r plus 1 a what now? An plus 1 instead of an plus 1. Xn plus r minus 1 will be xn plus r, right? So don't let me merge all of them together. So now we're having n plus r, n plus r, n plus r, n plus r, an, they are now uniform. Okay, then collect like term, the one with an plus 1 and the one with an in one side. So these two guys are having an plus 1, while these two guys are having an. So I'll make sure that this one is here. Okay, so that will be summation n from 0 to infinity. The one with an plus 1, I think they're having n plus r plus 1 as their common factor. Factorize them. N plus r plus 1 into, let's say, 2n plus 2r. I hope you get these two. Okay, then plus just 3, because you factorize this one. An plus 1 xn plus r is equals to, now move these two guys to the other side of the equation. Minus 2, what are they having in common? They're having n plus r. Okay, they're having n plus r in common, so we are going to have summation. Okay, n from 0 to infinity, n plus r is their common factor, then I open a big bracket, minus 2 into n plus r minus 1, and this one, this plus 3 also turn to minus 3. Do you get? Anx n plus r. So just make sure you factorize, or anyhow you want to do it. So n plus r, x n plus r cancel, summation cancel. After that, what do we have? We have n plus r plus 1 with 2n plus 2r plus 3 of an plus 1 equals to n plus r with this is minus 2n minus 2r minus 2 whatever. Well, I don't care, let me write it the way I like. Minus 2 into n plus r minus 1 minus 3 with an. Now divide both sides by this. An plus 1 equals to n plus r minus 2n plus r minus 1 minus 3 over n plus r plus 1 2n plus 2r plus 3, all with an. Okay, so this is our recurrence relation. After getting the recurrence relation, all right, now we are here. Now this is our nth term. Then you put your the solution of the initial equation, r at 0 and minus half. So when r is 0, we are going to have an plus 1 equals to, if r is 0, is 0, is 0, is 0, is 0. So this will be n into minus 2n minus 1 minus 3. Minus 2n minus 2, okay, and minus 3 over, if r is 0, n plus 1, okay. If r is 0, 2n plus 3 an. This one for one solution. Now let me do the other one here. Now when the initial equation for r equals to minus half, when r is minus half, an plus 1 equals to, if r is minus half, let me press calculator now. If r is minus half, minus half, minus half, minus half, okay. So this will be n minus half, n minus half into minus half minus 1, that's minus 3 over 2, minus 2n. What is minus 3 over 2 times 2? That's minus 3. So this one will be minus 3. Minus 3. You can just check me with calculator if I've made mistakes. So n minus half n minus minus half minus 1, that's minus 3 over 2. Minus half minus 3 minus 7 over 2. Oh, sorry, this is 2r. If r is minus half, that's minus 1. Minus 1 plus 3, that's 2. 2n plus 2. You get, if r is minus half minus 1 plus 3. Of what? Of n. And here, this one, this is minus 2n minus 3 minus 3. Well, this one will be minus 6 like that. Okay? Yes. So then you now count, for n equals to 0. If n is 0, what are you going to have? Automatically, everything is 0. A1 is 0. A1 is 0. Okay? Because if n is 0, the 0 that is here now, you turn everything to 0. And if A1 is 0, so the uniqueness of this solution is that all A's, A2, A3, A4, A5, all of them with 0, because when you do for n equals to 1, you are going to have something times A1 here, which will be 0. And you do it for 2, you are going to have something times A2, which is something of A1, that's 0. So A1 is 0, A2 is 0, all of them will be 0. Okay? Now let's move here. I think this one will survive. So for n equals to 1, for n equals to 0, A1 will be, if you put 0 here, put 0 here, put 0 here, put 0 here. So this will be minus half times minus 6. That is 3. Minus 3 over 2 times 2. Minus 3 of A0. Alright? That will be minus A0. You get? Then for n equals to 1, we are going to have A2. If you put 1 here, put 1, put 1, put 1. Okay? So what is everybody here will be minus 4. If you put 1 here, put 1 here, that is minus 2. Of what now? Of A1. So which is 2A1. And A1 is minus A0. That is minus 2A0. Okay? If I do it for n equals to 2 as well, it will be A3. If you put 2 here, well, I'll leave that one, viewers. I'll leave that one for you to complete. If you put 2 here, you have something times A1. So if that's the case, what will now be our solution now? Our solution is what? Don't forget, everybody here for this part, for this r equals to 0 part, they are all 0. So when you now write the general solution is y equals to summation n, summation a n x raised to power n plus r, n from 0 to infinity, and we have 2r, one is 0, the other one is 1. That is y equals to summation n from 0, a n x raised to power n plus 0 plus summation n from 0, a n x raised to power n plus minus half, n minus half. And if you expand this, it will be a naught x 0, a naught xn, all right, plus when n is 0, okay, a naught x 0, a1 x1, a2 x2, like that for the first part. Then for the second part, if you expand this, it will be a naught x, if you put 0 here, x minus half. If you put 1 here, a1 x 1 minus half, that's half. Okay, if you put 2 here now, 2 minus half, that's 3 over 2, x 3 over 2 plus dot 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 in that order. For the first part now, all our a1, a2, a3, a4, they are all 0 except a0. A0 is constant. So this guy is 0, this guy is 0, everything here is 0. So y equals to a0, and x raised to 0 is 1. Then you leave this one. Now write this. A0, what is a0 is a0. A1, what is a1? A1 is minus a0. What is a2? A2 is minus 2a0 x3 over 2. Like that. So when you now factorize a0, and that's all, y equals to a0 into 1 minus x minus half minus x half minus 2x3 over 2 is series. So it's continuous like that. So that is the final solution of this series. So one more example before I go. So I will jump some steps, so you guys should follow up. So this now 2x squared y double prime. So we already know that y double prime is what? Summation n from 0 to infinity n plus r minus 1 a n x raised power n plus r minus 2. Where do we get this one? Pause the video. What is the previous one that we've done? So xy prime, that's x summation n from 0 to infinity. Y prime is n plus r a n x raised power n plus r minus 1. Okay, and then you expand this. This will be minus xy, right? Minus xy, that is minus x times summation. What is y? Go back to the previous one. What is y? Y equals to a n x raised power n plus r. Okay, n from 0 to infinity. And this is a minus y. Y is minus summation n from 0 to infinity. Oh, yes, a n x raised power n plus r. All of them equals to 0. Okay, so what are we going to do? Indices, this one will cancel this. We are going to have 2 summation n from 0, n plus r minus 1, a n x raised power n plus r. X and this one will cancel this. This is x raised power 1. It will cancel this. Plus summation n from 0, n plus r, a n x raised power n plus r. Okay, this and this will be minus summation n from 0, a n x raised power n plus r plus 1, minus this, that's summation a n x raised power n plus r. Okay, n from 0 to infinity. All of them equals to 0. All right, so after that, how many sums do we have? We have 4. Which one is misbehaving? This third sum, n plus r plus 1. But what are we going to do here now? The two previous examples that we've done, they were having x raised to power n plus r minus 1. We have to shift them back. So we'll shift them back. But this time around now, what is here now is n plus r plus 1. Now, if I say let n equals to n plus 1 here, well, this sum, it will turn it to minus 1, and we don't want that. So what we are going to do is that I will count for, if I say let n equals to, okay, where are we starting from? From here, x and this, xy prime, x n plus r minus 1. We have this, we have this, we have this. Okay, now if I count for n equals to 0 and 1, if I count for n equals to 0, then this one will be a1, a0 and xr. Okay, now what we are going to do is that we will count for n equals to okay, let's say let n equals to n minus 1 here. Let n equals to n minus 1 in this third sum. I say let n equals to n minus 1. This sum will now start from 1. Okay, this sum will start from 1, and then we are going to shift this one to start with 1 as well. So let n equals to n minus 1 in the what? In the third sum. Is it the third sum? Yes, in the third sum. If n is n minus 1, what are we going to have? We are going to have 2 summation. We are going to rewrite all this one. N from 0, n plus r minus 1, a n x n plus r plus summation n from 0, n plus r, a n x raised power n plus r minus, if n is n minus 1, well, this one will now start from 1. Okay, 1 to infinity. This one will be a n minus 1. Okay, no, you are changing n to n minus 1. And this will be x what? If n is n minus 1, you know this will be n minus 1 plus r minus plus 1. That will be n plus r minus summation n from 0 of a n x raised power n plus r, all of them equals to 0. Okay, after that, then all these guys that are 0 now, you count for 0, so that all of them now will start from 1 together. So I will say count for n equals to 0 in the what? In first, second, and which one? And the fourth sum. If you count for n equals to 0, yeah, because we need initial equation now. We need initial equation. If n is 0, this will be 2r, r minus 1, a naught. Okay. If n is 0 here, plus r, a naught. Okay. And if n is 0 here, minus just a naught. Okay. All of them are having what? A Oh, x what? XR, because I'm saying n is 0. All right. Then this is where we are going to have our initial equation. You equate this guy to 0. If you equate this one to 0, XR is not 0, x raised by r is not 0. So this one will be 0. XR and A naught are not 0. So this will be 2r, r minus 1 plus r minus 1, A naught XR are 0. XR is not 0. Hmm? So this is initial equation. Our initial equation is 2r square minus 2r plus r minus 1 equals to 0. 2r square minus r minus 1 equals to 0. If you factorize that, 2, that's 2 times 1, 2, plus r minus 2r minus 1 equals to 0. R into 2r. Okay, let me just use calculator. Oh, so 2r plus 1 minus 1 into 2r plus 1 equals to 0. Yeah, your r will be 1 or minus half. Your r will be 1 or minus half, the initial equation. Okay. After getting the initial equation, let's just keep the solution of our initial equation. Put it to, this is your initial equation. Initial equation. Now go back to the sum. When you go back to the sum, what are we having after generating? Oh, don't let me clean the last sum, or else I'll start all over again. Okay, we are here now. This guy, we've count for n equals to 0. It means that this sum will now start from n equals to 1, right? Of n plus r minus 1, anx n plus r. This one too will start from 1 plus summation n from 1, n plus r, anx n plus r minus summation. This one is starting from 1 already. We've already shifted this one. An minus 1, xn plus r, and the last one here, n from 1, an xn plus r. Everybody equals to 0. Now, we are, all the series are now having the same lower limit. So factorize and get your recurrence relation. If you factorize this an parts, so I'm going to have 2, okay, summation n from 1 to infinity, this one, and this, okay, 2n plus r, n plus r minus 1, this, n plus r, and this minus 1. Okay, all of them are what? Are having an x n plus r is equals to the one with an minus 1. Bring it here, it will now turn to plus. Okay, an minus 1 x n plus r. So after getting that, cancel the what? Xn plus r guy, cancel the sum, then you have your recurrence relation. What is our recurrence relation now? This thing, 2n plus 1. Okay, I'll just jump that step. Divide both sides by this. If you divide both sides by this, you are going to have an equals to an minus 1 over 2n plus r, n plus r minus 1 plus n plus r minus 1. Okay, put all of them in one bracket. That is what we are going to use. But how many r do we have? We have 1, r equals to 1, and then we have r equals to minus half. So you know the drill. Just cut it into 2, do for r equals to 1 and r equals to minus half. So let me just partition it like this. So for r equals to 1 here, and for r equals to minus half here. So if r equals to 1, what will be our recurrence relation? An equals to an minus 1 over, if r is 1, 2n plus 1. If r is 1, n. Okay, if r is 1, this is 1 minus 1 plus another n. Okay, now for r equals to minus 1 over 2, well, I'll use calculator here. An equals to an minus 1 over, r is minus half. Oh, this will be 2 into n minus half. If r is minus half, minus half minus 1. Oh, I'm saying rubbish. Yes, minus half minus 1 is what? Minus 3 over 2. Yes, n minus 3 over 2. And if r is minus half minus 1 again, minus 3 over 2. So it is easy to make mistake in this kind of thing. So just check it again if what I'm doing is right. But it's right. Okay, it's right. Then you count now.
when n is 0. Or when n is, I'll start from n equals to 1 this time around. When n is 1, this one will give us a1 equals to, if n is 1 here, this will be a0 over, n is 1, 1 plus 1, 2, 2 times 2, 4, 4 times 1, 4, 4 plus 1, 5, you get. Then when n is 2, a2 equals to a2 minus 1, a1, if n is 2, 2 plus 1, 3, 3 times 2, 6, 6 times 2, 12, 12 plus 2, 14. And what is a1? a0 over 5. That is a0 over 5 times over 14, okay? That is a0 over 14 times 5, 70. You can do it for n equals to 3. That would be a3 equals to, well, you two should do that one. Press calculator, you get it. Now, start for n equals to 1. What is a1? a0 over, now if n is 1, oh, everybody here is minus 1. That is minus a0. Then for n equals to 2, a2 equals to, put 2 here, a1 over, put 2 in all of 2 minus a0. So this a1, change it to minus a0. That is minus a0 over 2, because all our answer will be in terms of a0, 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 a0 for Frobenius method. But for power series, the answer will be in terms of a1 and a0. Those are the two boundary conditions. So, well, for n equals to 3, a3, 3 minus 1, a2 over, okay, I'll put 3 this time around. Oh, 9. And a2 is what? Minus a0 over 2. Minus a0 over 2, then over 9. That is minus a0 over 18. Well, you can generate more. So then write your solution, that's all. You write your solution, y equals to what? What's our solution? Summation a n x raised to n plus r. And we have two r. One r is 1, the other r is minus r. So split them. So it will be y equals to summation n from 0, a n x raised to power n plus 1, plus summation n from 0, a n x raised to power n. The other one is minus half, n minus half. Okay. So now expand and write your answer. So y equals to what? Summation. If you expand this, this will be a0 x n plus 1, a1 x, oh, yeah, n is 0, x just 1. If n is 0, this will be a0 x 0 plus 1, x1. Now if n is 1, it will be a1 x 1 plus 1, a1 x2. If, okay, if n is now 2, if n is now 2, it will be a2 x2 plus 1. Yes, a2 x3, like that, like that. Then for the other guy here now, for this guy, when n is 0, a0 x minus half, because if 0 is here, it's just minus half, plus a1 x, if n is 1, 1 minus half is half, okay? a2 x 2 minus half, that's 3 over 2, x 3 over 2, plus dot 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 and stop. Then y equals to okay, a0 x, what is a1? a1 is a0 over 5 x squared. What is a2? a2 is a0 over 70 x cubed, plus dot dot dot. Then plus a0 is a0 x minus half. A1 is what? A1 is minus a0 x half. A2 is what? Minus a0 over 2 x3 over 2, like that. Then factorize a0 into x minus, plus x squared over 5 plus x cubed over 70 plus dot dot dot. Then here you factorize a0 as well, x minus half minus x half minus x3 over 2 over 2, like that. So that is how the solution will be. So basically that is how we are going to solve problem on Frobenius method. So thank you.